Example 2.3.7, two loads are supplied at 200 volts RMS and can be described as follows. Load 1 is 15 kVA at 0.6 lagging, and load 2 is 6 kVA at a leading power factor of 0.8. The loads are served through a distribution line with a complex impedance of Z line equals J1 ohm. Find the phasor voltage of the supply. So, let me get my pen up here. The answer to this starts by constructing the system model and making sure we know what's going on here. So we were told that there's two loads. We should know by now that loads in power systems are parallel. So we've got two loads, load 2 and load 1. So we've got those parallel loads, and we were told that they are supplied at 200 volts RMS. So that means if we were to measure the parallel voltage across the loads, we're going to get 200 volts, right? We were said that they are served through a distribution line with a complex impedance of J1. So we'll just analyze that as J1 ohms, and then we've got our voltage source that we've got here, V source. So usually in power systems, when they tell you the total impedance of the line, that's a lumped value. So you can see that I put a J1 in there for the lumped value of the top line and the return line. That's pretty typically how that's specified. A little note that impedance line models for very short lines are usually a series resistor and inductor. If they're really short, the resistance becomes almost negligible. So what this is indicating is that this is an extremely short distribution feeder. I know that because it's only got a reactance associated with it. So we draw that little system model, and we need to solve the solution. And we're trying to find out what is the voltage, Vs right here. What is that? That's what it's asking. Find the phasor voltage of the supply. And that supply generally would be the output terminals of a transformer in a power system. So the solution method is that if we know the current here, then we can find the voltage drop across the line, and we find out that the source voltage is just equal to the load voltage plus the voltage drop across the line. So it's pretty straightforward. We can rewrite that equation as the source voltage is equal to the load voltage plus the current flowing in the line times whatever the impedance of the transmission line is. So that's the general approach to one of those. So in that equation, only I line is unknown. We need to solve for that because we have V load at 200 volts, and we know the impedance of the line is 1 ohm reactive. So we need to solve for I line. Now, the information we were given that will help us solve for I line is power information. So we need to be able to manipulate this stuff appropriately. So we need to really, what we're trying to solve for, I line. What is the current? So I line right here is going to be the combination of the two currents flowing to the loads. But because we've got power information, we can just go ahead and lump them together. We don't have to calculate those two currents independently. We could, that would be one approach. We could calculate I1 and I2 and add them together. That's fine. That's not the approach I'm going to use. I'm going to lump L1 and L2 together via power. And to do that, what that means is that the total apparent power in the circuit is going to be the apparent power of load 1 plus the apparent power of load 2. Remember, in these circuits that power is always additive, whether it's in series or in parallel, it doesn't matter. We always just add. And then I can solve for I line if I know total circuit power from our power equation, which is just going to be the total apparent power divided by the voltage across the loads, And then remember, we need to take the complex conjugate to take care of the angle that we have. So we need to figure those out. Next, what we need to do is we need to figure out what S load 1 and S load 2 were, because they were given to us in different formats. They weren't given as polar, they were given as a magnitude and a power factor in both cases. So we need to convert that information over. So this problem is also testing your understanding of the concept of power factor. Remember that in the power triangle it looks like this. We've got S as the hypotenuse, real power is the base, reactive power as the height of the triangle. This here is called the power factor angle, and cosine of theta is equal to the power factor. Another way to say that is the power factor is equal to the ratio of real power to apparent power. The reason we like that is because we can use this format right here to say that the power factor angle is equal to the inverse cosine of the power factor. And typically how customers state their power needs are either real power at a power factor or apparent power at a power factor. Those are the two common ways that it's done. But that formulation there is going to allow us to determine what the angle of S is in both cases. That way we can do the vector addition that we need to determine S total. So I'm just going to call S load 1 just S1, and we were told that it was a magnitude of 15 e to the third, and then to get the angle it is just the arc cosine of the power factor, which in this case was 0.6. So S1 from that calculation is 15 e to the third at an angle of 53.13 degrees, and that's apparent power, so it's measured in units of volt amps. So a similar thing needs to be done for load 2. So we were told that it was 6 e to the 3, and it was at an angle of the arc cosine of 0.8. Now I want to scroll up a little bit and talk a little bit about lagging and leading. A lagging power factor means that the circuit is inductive and the power factor, the power triangle is in the first quadrant of the complex plane. But we see that we've got a leading power factor for load 2, which means its power triangle looks like this instead. And so what we have to take away from the fact that it's a leading circuit is that the power factor angle in this example is negative. So that's why we get the negative, is because this is a lagging circuit, which is a positive power, and this is a leading circuit, which is a negative power. And so that's going to give us a total power of load 2 of 6 e to the third at an angle of negative 36.87 degrees. That's apparent power, so it's measured in volt amps. So make sure you get your power angles right depending on whether the circuit is lagging or leading, where lagging means inductive, and that means it's a positive power factor angle, and leading is negative, and leading is negative. So now what we need to do is just determine I line. That's going to be equal to 15 e to the third angle 53.13 degrees plus 6 e to the third angle negative 36.87 degrees. We need to divide that by the voltage, which was 200. Since we don't know the voltage anywhere else in the circuit, we're going to take that as our reference. The load voltage in this case we will take as the reference, and then we got to take the complex conjugate of that. And so what you should find is that you get a line current of 80.78 at an angle of negative 31.33 amps for the total current being used to deliver the power to those two loads. Right. So from the formulation that I set up for you earlier, what we now need to do is calculate the source voltage from the load voltage plus the line current times the distribution line impedance, which was J1 ohm. And so we get a voltage of 251.64 angle 15.91 degrees volts. So if we were to quickly redraw that circuit, we've got .64 angle 15.91 degrees, and we've got 200 angle 0 degrees. Now some people don't like to have the load as the reference in a circuit. They would rather have the source as the reference in a circuit. It really doesn't matter because it all kind of comes out in the end. The technique I showed here is really frequently used when the load is known and you're trying to solve for the supply. But just remember that phase shift is a relative term between waveforms. And so right here what I have said is that the source leads the load by 15.91 degrees. You could also say the load lags the source by 15.91 degrees. So it would be just as correct if you were to write V source equals 251.64 angle 0 degrees and V load is equal to 200 angle negative 15.91 degrees. That would be fine. If you did that, you'd have to redefine I line as well as 80.78 at an angle of, we need to take 15.91 off of this, so it gets more negative 47.24 amps. That would be fine too. Any of those formulations would work because of the relative nature of phase angle.